Now, can we find a place where voltage equals zero? Is there a place where voltage equals zero? So, we know V will equal zero at infinity. We'll be infinitely far from both charges. We don't bother to write that one down because we know it. It's not interesting. We don't have to worry about direction since V is a scalar. And we can reuse one piece of reasoning, which says we won't find a point where V equals zero over here because, again, we're always closer to the larger charge. This will never be able to match it. So the only possibilities are in between the two charges and on the outside, on the right side of the smaller charge. Let's look for that one first. We say V equals 0 is to the right of the smaller charge. It's x away. That means, again, it's 1 plus x away from the larger charge. Potential is kq over r. Put these things in. I can, again, divide by k and nanocoulombs and 5 and get this. We cross multiply. This one we can solve pretty quick and get that the position is 0.667 meters to the right of the smaller charge. So the potential from the 25 nanocoulomb charge, we've got 1 meter plus that on the bottom, k times 25 nanocoulombs, get about 135 volts. For the negative charge, and that's what this would be negative here, k times 10 nanocoulombs over 0.667, again 135. Is there a point in between the charges where V equals 0? Again, we'll say it's x away from the smaller charge. This time that means x this way to the left. So if we say that, we have k times 25 nanocoulombs over 1 minus x plus k times negative 10 nanocoulombs over x equals 0. We shuffle them around with some algebra. We move this one across the equality here, divide by k and 5 nanocoulombs, and we get this. Cross multiply again, we get this. So 0.2857 meters to the left of this charge. So we get 315 volts there. If we're 0.286 or whatever meters to the left of the small charge, we're 1 minus that to the right of the big charge. 315 volts there. So it works. Now, what's the real meaning associated with this? Potential is PE per charge and E field is force per charge. This means if we put a charge where E equals 0, it'll stay there forever because the force on it is 0. On the other hand, what if we put a charge at a point where V equals 0? That means we can move it to that point from infinity and it won't cost anything. We won't get any energy out of it. We won't have to put any energy into it. So again, if we want to try and model this with gravity, a positive charge is like a mountain and the negative charge is like a valley. We can find a place between them where height equals 0, the potential equals 0. That doesn't mean if we place a bowling ball there, it'll sit still. The same way, if we find a place where the ground is flat, so the ball will sit still, that doesn't mean we've found a place where the height is equal to sea level. What if we did this with two charges of the same sign? Here, we look at our E fields again. The blue is pointing away from the blue charge everywhere. The red is pointing away from the red charge everywhere. We certainly can't get an E equals 0 on this side because they're both pointing to the right. Can't get one over here because they're both pointing to the left. The only place E can be 0 is in between them, and we'd go through the same procedure to solve it. Here, we won't see any place where potential equals 0. Why is that? Well, if we have a single charge that's positive, the potential is going to look like the height of a mountain infinitely high, but the height slowly drops to 0 infinitely far away. If both charges are the same sign, there's no place other than plus or minus infinity where potential would be 0. You can look here for a plot of what voltage would look like along the line, where we have infinitely high peak here, going down to near 0 but not reaching it, infinitely high peak here, and again dropping off.